First of all, I see that we have all gathered here in accordance to our protocol, so we can begin. I had to mute everyone but myself for this part of the protocol, and later during discussion you can unmute yourself or raise your hand. So let us begin. Dear candidate, respected members of the committee and others who are present, I hereby determine that today, October 1st, 2020, the doctoral candidate Bruno Antulov-Fantulin, Master in Aeronautical Engineering, defends his doctoral dissertation with the title Air Traffic Complexity Model based on Air Traffic Controller Tasks, which was made under the mentorship of Associate Professor Biljana Juričić. I establish that all members of the committee and the doctoral candidate are present, that all legally prescribed conditions on the basis of which the procedure is conducted have been met, and that full publicity of the defense has been ensured. The doctoral dissertation will be defended before a committee of 3 members composed of Assistant Professor Tomislav Radišić from University of Zagreb Faculty of Transport and Traffic Sciences, Associate Professor Biljana Juričić, University of Zagreb Faculty of Transport and Traffic Sciences, and Associate Professor Cem Cetek, Faculty of Aeronautics and Astronautics, Eskisehir Technical University in Turkey. This committee was appointed by the Faculty Council of the Faculty of Transport and Traffic Sciences at its 25th session held on September 22nd, 2020. Now, I will read the curriculum vitae of the advisor. Biljana Juričić is an associate professor in the field of technical sciences, field of transport and traffic technology, air traffic branch. She is the head of the chair for air traffic control at the Faculty of Transport and Traffic Sciences, University of Zagreb. Also, she heads the Croatian Air Traffic Control Training Center. She is the author or co-author of numerous scientific papers published in international journals and in proceedings from international scientific conferences in the field of air traffic management. She earned her Ph.D. in technical sciences in the field of transport and traffic technology at the Faculty of Transport and Traffic Sciences. As for the candidate, Bruno Antulov-Fantulin graduated in 2013 at the Faculty of Transport and Traffic Sciences, University of Zagreb, and earned the title Master of Aeronautics. In December 2014, he was employed at the same faculty as a teaching assistant at the Department of Aeronautics. In 2015, he enrolled in the postgraduate doctoral study at the Faculty of Transport and Traffic Sciences, University of Zagreb. I will now read an abstract of Mr. Antulov-Fantulin's doctoral thesis as an introduction to his defense. Existing models for determining air traffic complexity that are based on air traffic controllers' subjective assessment are not consistent due to possible deviations in complexity assessment. The aim of this research is to create a mathematical model for air traffic complexity which is based on the air traffic controller tasks. The model uses the data on area radar air traffic controller tasks that are defined according to the traffic situation. Certain air traffic controller tasks, such as conflict resolution, are perceived as one task, but they actually represent a set of multidimensional tasks that need to be defined as multidimensional in order to be used later in the mathematical model. Moreover, the existing models for determining air traffic complexity, which use the subjective air traffic controller assessment, also include the problem of subjectivity resulting from the learned mode of operation in a given airspace. This research introduces a new approach to designing a model for determining air traffic complexity, which is based on defining area radar air traffic controller tasks for the given traffic situation. Using machine learning, inputs such as defined air traffic controller tasks and complexity scores gained through comparison methods were used to develop a new mathematical model for determining air traffic complexity. The validation of the model was carried out by the same comparison method using the traffic situation data on a different airspace. Now, Mr. Antulov-Fantulin, I invite you to present your doctoral dissertation, and please do so in 30 minutes or less. The floor is yours.
Thank you, Chairman. Thank you, Tomislav. Let me just share my screen. Give me a second. And please tell me when you see the presentation.
We can see it.
Okay. So, dear all, thank you for coming to my doctoral thesis defense. Today I'm going to represent you a novel model for air traffic complexity based on the air traffic controller tasks, under my mentor and supervisor, Associate Professor Biljana Juričić. So the presentation outline will start with introduction to the complexity, some of the problems it ties to, the idea how we plan to solve those problems, research and the experiment, results of the research, and the conclusion of the research and the results. So without further ado, we can start with introduction and what is complexity. So complexity has turned out to be very difficult to define. The dozens of definitions that have been offered all fall short in one respect or the another, classifying something as complex which we intuitively would see as simple, or denying an obviously complex phenomenon the label of complexity. So how does complexity tie to the air traffic complexity? Well, traditionally, traffic density has been the single factor most associated with complexity. However, it is increasingly clear that density by itself is an insufficient indicator of the difficulty a controller faces. So can we say that air traffic complexity is a subjective construct? Let's say, for instance, we take a random person and give them a task to move a heavy object from one place to another. A young, strong individual might say it is of low complexity task, while an elderly person might say it is high complexity task to them, while a third person might just say it is of a medium complexity task. And with that, we are introduced into a problem where, as well, air traffic controllers assess complexity subjectively. And regarding the problem with complexity in aviation, it is tied to the airspace capacity. So for this example, we'll take a randomly shaped airspace volume. And we all know prior to the COVID pandemic that traffic has been increasing each year. And the problem with that is that for a certain volume of airspace, you at a given moment, you just can't take any more aircraft. So ANSPs need to put regulations which generates delay and penalization for the given ASP, Air Navigation Service Provider. So what we all want to do here is increase airspace capacity, and which in general generates revenue for the NSP. But in order to be able to increase airspace capacity, we first need to look at what are the constraints for airspace capacity. So we all know that airspace capacity is directly tied to the air traffic controller workload, and workload is directly derived from the air traffic complexity. So the consensus view among ATC research and operational communities is that complexity drives controller workload, which in turn is thought to ultimately limit the airspace capacity. So what is the link between complexity and workload? So some source factor for the air traffic complexity are the air traffic pattern and sector characteristics. And through some mediating factors such as equipment quality, individual differences, and controller cognitive strategies, we derive the air traffic controller workload. So complexity is not a synonym for workload, although it has been proven multiple times that the increase in complexity results in increase in workload, which in turn limits the airspace sector capacity. So the problem here is that many researchers tend to try to increase airspace capacity through workload, but not directly researching how it affects complexity, because complexity is direct linked to the workload and the airspace capacity. And some of the problems here are also that models are usually tied to a specific airspace, and some subjective assessment given by the air traffic controllers are not consistent. And complexity indicators sometimes can be uncontrollable in different environments. Altogether, complexity is hard to approximate equally for everyone. So with that, we reach the ideas, some of the issues and solutions that we mentioned here. So the first issue, we try to solve it with air traffic controller tasks. Precise definition of controller tasks based on the conflict resolution parameters cover traffic situations in more detail than a fixed number of indicators and could easily be implemented for operational purpose, let's say. About the airspace bounding problem with models, it is common for a person to link the learned experience with the new ones. The same goes with air traffic controllers, where previously learned airspace knowledge and gained experience cause an error in complexity assessment and scoring. So to mitigate this problem and to be able to use the model on a different airspace, controllers were tested on the unfamiliar generic airspace. For the third issue, we saw earlier now that air traffic complexity is a fundamental driver of workload, but that the connection between complexity and workload is not straightforward. It is mediated by other factors. So by putting the controllers to assess the complexity on the real-time simulator, it can be difficult for them to distinguish the air traffic complexity from the workload. So to solve this problem, controllers were assessed the air traffic complexity by using paper static images. And finally, the inconsistency between controllers. Several researchers have stated that some of the controllers give same score for different level of complexity. And that is a problem if you want to use that to model a complexity model. And basically to solve this problem, controllers were given two different traffic situations at the same time. During the experiment, the controllers compared two traffic situations and evaluated which one is more complex, thus eliminating any inconsistencies where controllers would grade different traffic situation with the same complexity score. So now we are, when we introduce the problems and the ideas here, the research methodology started with design and development of airspace and design and development on controller tasks. Also traffic situations, and with that the extraction of the task could commence. For the experiment, prior to the experiment, briefing of the definitions of complexity and workload was done to the controllers. Assessment and ranking of traffic situations by the controllers were done, and grading the ranked traffic situation as well. When we gathered all the data, model development could commence and model validation was done in the end. For the airspace, this generic airspace, S0, is a hexagon-shaped, diagonally in 100 nautical miles in distance and vertically 10,000 feet. The extended airspace S1 is formed by making a homothetic transformation for 50% for each point from airspace S0. These traffic situations are defined on a generic airspace to ensure the possibility of using the model on a different airspace, and to avoid air traffic controller subjective assessment for the already known traffic situations and airspaces. During the development of the traffic, air traffic situations were carefully created so that the air traffic is distributed into three main categories: low, medium, and high complexity traffic, where in each category there are 40 traffic situations, and each has the exact number of aircraft that triggers a specific controller task. So there are 120 unique traffic situations developed and divided into 6 groups. Each group consists of 30 traffic situations, from which 18 are unique to that group, and 12 traffic situations are the same and repeated into all 6 groups. Repeated traffic situations are created intentionally in order to better evaluate the air traffic controller assessment between themselves. So with that, we've reached the air traffic controller tasks. A detailed and comprehensive definition of the tasks were defined. It was important to define these tasks in a way that they are not affected by the air traffic controller's decisions and resolutions of specific conflict. This is one of the main factors that will contribute to a good overall feature selection for model training, because if it is possible to define the tasks to not take into account the unpredictability of a human behavior, in this case, air traffic controller resolution of the task, they could overall better evaluate the air traffic complexity. So first 4 tasks can be subclassified into 3 categories by their geometrical parameters of same crossing and opposite track. And furthermore, all 3 previous subclassifications can further classify according to their geometric and physical parameters, such as distance between aircraft, speed, converging angle, distance from conflict point, freedom of movement for the first and second aircraft to the left, right, above itself, below itself, and distance to the exit point. And as you can see, all the tasks are categorized with codes, and effectively this is in the end solved as binary problem, where we can solve it as all as zeros and ones. And all the possible permutations of the tasks are 1.9 octillion individual tasks. So let's take a look at random traffic situation and what task can be given for this example of 3 aircraft. So first, what we'll be doing is that the controller would screen the traffic, And intuitively, we will see the number 7 task, non-interactive complex screening for Qatari and Croatia aircraft. Again, we have another task of number 7 non-interactive complex screening between Qatari and Lufthansa. And then we have a number 5 interactive complex screening between Lufthansa and Croatia. And in the end, we see now that we have a conflict between those two, and fourth and final task for this traffic situation is coded as such, where the code stands for C for number 1 conflict resolution, another second C is for crossing track, 4 is the distance between 31 and 40 nautical miles, and so on and so forth. And with that, we reached experiment data gathering. So for the experiment, it is vital to state the process of gathering the data, since it is one of the factors that contribute to good results in the model. Earlier was stated that there are 120 traffic situations for assessment and divided into 6 groups. There were 3 air traffic controllers per group, so in total 18 controllers were tested. So it is important to always give the tested air traffic controller a set of 2 traffic situations for complexity assessment. In this way, air traffic controller is forced to choose which of the 2 presented traffic situations is more complex. And during the experiment, the merge sort algorithm is used to rank the traffic, and the input from the air traffic controller was taken as a sort list rule for the merge sort. So by ranking them in this manner, it is impossible that 2 traffic situations have the same complexity score. Using this approach, any consistent assessment by the air traffic controller is eliminated, so that at the end of the validations, there is a clear rank from the lowest to the highest air traffic complexity. Furthermore, to establish a clear grading system, controllers needed to grade the ranked traffic situations into classes of complexity scores from 1 to 5, where 1 is the lowest and 5 is the highest complexity score. Based on the controller's complexity ranking and scoring, linearly interpolated grades are assigned to each ranked traffic situation for each controller. As a final step, controllers were asked to determine where would be the point where they believe that the sector should be divided so to reduce the air traffic complexity. And with that, we have all the relevant data that we can now start with the model development. First, we started with exploratory analysis, where we done correlation between features, histogram of feature distribution, principal component analysis. With good exploratory analysis, we've done feature construction. We've taken 69 tasks plus 5 aircraft count variation features, in total 74 features, and in total 17 models with different features were tested. So for the target variables, a pairwise comparison for merge sort results was used, and controller grades. And for statistical modeling, a logistic regression was used for pairwise comparison, and Bayesian ridge regression for controllers grades. And for the model validation, we've done bootstrapping, cross-validation, model compared to the controller, testing a model on a new airspace, cherry picking, and sector optimization. So with that, we've reached the point with the results. And here all the rankings for all the 120 traffic situations can be seen ordered from lowest complexity score to highest. So ranking by mean interpolated grade from lowest complexity to the highest complexity is compared with the model's 90% interval confidence. It can be seen that different air traffic controllers had a difference in opinion for the same traffic situation, which only confirms the theory that the complexity is a subjective construct. Furthermore, models' interval confidence is also not 100% accurate. By the analysis, it is clear that the interval is almost all the time in the range that the air traffic controllers would estimate, but for some situations, it can have greater deviation than the particular air traffic controller. But it is important to mention when looking at the overall situation, model will have less deviation from the mean interpolated grade than the air traffic controllers. So to take a closer look, we'll just look at the repeated traffic situations here. And the graph perfectly shows and confirms the earlier mentioned statement. It can be seen that the model's 90% confidence interval is always less wrong than the complexity estimation than all air traffic controllers were for each traffic situation. So this becomes apparent when more air traffic controllers start to give complexity estimates for the same traffic situation. And when we reach the point where we want to compare the model to the controllers, we done it in two ways. We compared how much controls grade differ from the mean interpolated grade. And we can express this into two ways, the average and extreme case. In the average case, where an average difference is taken from the mean grade across all 30 situations that a particular controller graded, and the extreme case where the maximum absolute difference is taken from the mean grade among all 30 situations that a particular controller graded. So for each of these cases, one value per controller was obtained, and these are shown with the red vertical lines on the slide. This statistical model can provide a distribution of estimates for each of these cases, and these distributions are plotted on the same graphs. So distributions are calculated by building 1,000 separate statistical models on a 1,000 random subset, each containing 30 situations, the same number of situations that the controllers had to grade. So when we apply the same technique on the new unseen airspace, this final evaluation of the statistical model was performed on a separate set of air traffic situations, which are defined on a completely new airspace. And these are not used for training of the statistical model. So the same rule applies here. For the validation of the model on a new airspace, the same testing methodology was used, but only each containing 6 situations, the same number of situations that controllers use for the validations here now. And we can see in the distribution that, let's say for the max difference for each controller is that the model, the maximum deviation from the mean interpolated grade is only 1.5, while we have 2 most extreme controllers above that range. And for 0.1% cases, the model would even give the better estimate than the utmost controller. And we have some negative differences and positive, but we can discuss it further in the discussion. So we have more time to go through the results. So for the new airspace, this is a plotted graph of the model and the controller's grading system for each individual situation for the new airspace. So a ranking by mean interpolated grade from lowest complexity to the highest is compared with the model's interval. It can be seen that the different air traffic controllers had a difference in opinion for the same traffic situation, but the model's interval confidence is also not 100% accurate. By analyzing the results, it is clear that the interval is almost all the time in the range that the air traffic controllers would estimate, but for some situations, it can have a greater deviation than the particular air traffic controller would grade it. So when we observe and examine a V5, for instance, it can be seen that the model's distribution is extremely on spot to the mean interpolated grade. The reason behind the good results is the fact that the V5 was estimated by the 9 air traffic controllers compared to the usual practice of 3 controllers per traffic situation. Also, it is important to mention when looking at the overall situation model, we'll have less deviation from the mean interpolated grade than the air traffic controllers would have. And finally, you can go anywhere with the correlation. We make some correlation assessments between model estimates and controllers estimates. The model was trained on a 100% original data set and was tested on around 20%. This process was repeated 600 times. When Pearson coefficient correlation of the model complexity estimates is compared with the air traffic controllers estimates, results of 0.867 is obtained. Now for industrialization application, cherry picking and sector optimization. So for the cherry picking, it was done by a wrapper approach where by excluding a certain aircraft, it can be seen how much does the complexity change. The aircraft whose removal leads to the highest reduction in complexity are considered the most complex. So the advantage of this wrapper method is compared to extracting complexities directly from the coefficients of the regression is that this method is model agnostic and can be performed even with nonlinear models. And on the top right, on the top of the table, we have the most complex aircraft, and removal with with its removal, we see a complexity difference. On the right, we see some of the tasks, but we can later on discuss it in further detail, what this means and how it can be applied with some measures as well. So for the sector optimization, after controllers provided the final complexity ranking of all the 30 traffic situations, they were asked to mark a position in ranking after which they would suggest an opening in a new sector. All air traffic situations below that mark were considered as 0, and all situations above it as 1. As each situation was evaluated by multiple controllers, the graph shows a total number of zeros and ones obtained for each individual situation. And there are two ways of how this information is encoded. We have a discrete and interpolated way. For the discrete, there's only information on whether a controller classified a certain situation as 0 or as 1. And the mean value is then calculated for each situation across all controllers that graded a particular situation. Value can range from 0 to 1. And in the interpolated case, distance from the new sector marking is calculated for each situation, taking into consideration interpolated grades calculated for each controller and each situation. So mean value in the calculated for each situation across all controllers, evaluated this situation. In theory, this can range from -5 to 5, but in practice, it can be seen that it's from -3 to 2. So in the conclusion, first, we can conclude that the model can calculate complexity score equally and in range as the air traffic controllers would calculate them and assess them. It can cherry pick the most complex aircraft out of the traffic situation and using as well sum measures. It can make sector optimization based on complexity. And the most important part, it can be used on a new airspace, unseen airspace. All these four conclusions are really important because this model can be used in operational purposes, for the operational purposes. And we can say that the model is learned once and apply anywhere. With that, I would like to thank you for your attention, and I would like to ask you to ask as many questions as you would like, because the presentation could not go into much depth because of the time frame for this defense. Thank you.
Thank you, Mr. Antulov. Please mute your microphone if you can now. Okay. Now I would like to ask members of the committee to ask their questions. First up, we will give the floor to our external member of the committee, Professor Cem Cetek. So, Professor Cetek, please ask your question. It could be that we have some issues with connection with Professor Cetek. So I will give the floor to Professor Juričić for her question.
Okay, thank you very much. Bruno, thank you for your impressive presentation. Although I have read the thesis, still it is very interesting to see your explanation of your approach to this problem and to development of the new air traffic complexity model. So my first question will be regarding development of your novel method. You didn't have much time to say about it. So maybe I would like to ask you, why did you use this approach with static images of traffic situations instead of using real-time human-in-the-loop simulations. And also, regarding that similar question, what parameters were used to design all of these traffic situations? You said there were 120 situations, and how did you ensure to activate all necessary tasks that will be used later in the model development?
Okay, thank you, Professor. So for the first question regarding the paper static images. So maybe if I'll go slide prior, just a second. So this is the reason why, because if we put, let's say several researches that being tested the complexity on the human-in-the-loop simulations, always calculated the complexity with some disadvantages in a way that there are some restrictions that the model is tied to the airspace, or the model is tied to specific indicators, or in the end, the model is only tied to this certain specific people. And in order to implement it on a different environment, you need to recalculate and adapt it. And this is the first reason why we've done it. Here you can see on the slide the reason behind why I didn't want to put controllers in the human-in-the-loop simulations, because ultimately, if you put a person on a simulator and ask them to assess the complexity subjectively or unconsciously, they just might assess the controller workload. Why? Because there's these mediating factors, such as human-machine interaction, equipment quality, that can influence the workload, increase in workload, and the controller might just give you the wrong input based on those factors and not on the factors of air traffic pattern and sector characteristics. So if you put them, let's go back to the to this. So if you put them to the paper static images, they have as much time as needed to assess the complexity. They are not under pressure to work the traffic, and they are not they don't have any mediating factors such as human-machine interaction that can influence the workload instead of the air traffic complexity. So I believe that assessing complexity through human-in-the-loop simulations is not the best approach for experiment if you want to detect air traffic complexity. The next question was regarding the
design of traffic situations.
Design of traffic situations. Okay.
How did you ensure to generate all necessary tasks so that your model will be a strong model with background of all necessary air traffic controller tasks regarding different pre-conflict resolution situation? So the answer is directly linked and tied with the controller's tasks, because what I wanted to do is make some kind of indicators, in this case air traffic controller tasks, that would not be affected by the person controlling the traffic. That's the first thing that I wanted to do here. So what I first done was research all the possible air traffic control tasks that they are doing, and examine the real-time traffic that was going in several airspaces. And based on that, I've made the tasks that could overall fit any situation for any airspace. And with that, I started to design the traffic situations. The main goal was also to bear in mind of the level of complexity for each traffic situation. So there were 120 traffic situations, and divided into 3 groups of 40 traffic situations per low, medium, and high complexity. And each were carefully
addressed and issued with what traffic pattern should trigger a specific air traffic controller task.
Okay, thank you. That was my first question.
Thank you.
Okay, thank you, Professor Juričić, and thank you, Mr. Antulov, for answering this question. I see here Dr. Kopardekar has raised his hand and patiently waiting to ask you a question. So I would like to give floor to Dr. Kopardekar to ask his question or a comment.
Thank you. Can you hear me? Okay.
Yeah,
yes.
We hear you very well.
Well, good morning. Thank you for inviting me for the Ph.D. dissertation. It's been a long time for me to attend a dissertation on complexity topic. This was something I also studied in 2003, early 2000. So this was exciting to see work going on this area. Thank you. I have several questions, but Bruno, thank you for a good presentation. So I will ask the first question. In the past, we have considered complexity as an objective metric and the response from the controller as a subjective metric. So what we used to characterize as a workload. And in your thoughts, you kind of mentioned complexity as more subjective. So I wanted to get the subtlety from your perspective before I go to the next question. What makes your thinking complexity more subjective than an objective? What we were thinking in the beginning is that complexity is the situation that is related to the traffic and the geometry, and the response from the controller is more objective because there is a subtle difference among the different controllers as to how they would handle it and what their feeling of complexity is, and could be high or low. So that would be the workload. So can you, yeah.
Yeah, thank you, Mr. Kopardekar, for attending and for the question. So basically, what I believe and want to do is to make the complexity objectively. So these are the features, the tasks that are defined that should categorize air traffic pattern and sector characteristics that controller perceives subjectively to make it as an objective measure of complexity. So why did we start with subjective measure? Because prior to this research, I made a review of all the relevant models for the air traffic complexity, and mostly the ones that excluded air traffic controllers from the loop. In the end, somehow did not find the approval of the operational purpose from the air traffic controllers, because ultimately they were not giving the good results all the time for the air traffic controllers. And what was the problem there? I wanted to see, when you ask a controller, can you tell me what's the complexity of this particular traffic situation? One controller will tell you one score, a second controller will give you, for the same traffic situation, completely different score. So there we found the link that it is subjectively. Just a second. Another reason that we can confirm that they think subjectively for the same traffic situations is if you take a look to the left traffic situations, the blue dots are air traffic controllers. And you can see that they do not tick the same all the time for the same traffic situation from 1 to 5 of complexity score. And that is also in direct link that they think that the complexity is objective. But what we're trying to do is take their inputs, try to maximize to remove the subjective construct here. By using merge sort algorithm and to force them to choose always between two traffic situations. With that application, we force them to remove this subjectivity, and with that, we can use these scores as target variables to make objective measure of controller tasks for air traffic complexity.
Yeah, okay, thank you for your clarification. I think we are saying the same thing. It's just you may be asking them to rate complexity. Yeah, in the research I did a while back, we asked them to rate their workload in response to the situation we showed, and then we mathematically computed the complexity. So I think it's a similar thing what you asked them to rate complexity. So I get it. Thank you. And the second question, the second question I have is you kind of attributed complexity to individual aircraft, and your previous chart also shows, right? The complexity is based on individual difference, it's the traffic pattern, and few other factors, equipment and all that. So assigning complexity to individual aircraft without regard to these other factors, what are your perspective on that? That seems interesting in the sense that complexity to that aircraft doesn't exist if there is no surrounding traffic and such, right? So are you referring to the ability to resolve a potential conflict, or are you referring to situation where that aircraft has to get out of the way of others, or what is that singular factor that is making that particular aircraft higher complex?
The honor is mine.
So I'm not sure if I understood the complete question here, but I found some lines, but if I misunderstood you, please interrupt me and ask the question again. So what I think I heard is that you asked me, how can I identify from the traffic situation which aircraft is most complex, right?
Yes, that's pretty good. I think you had another chart where you showed that, but one particular aircraft given 3.48 or some kind of complexity.
Okay. This one.
Yeah, right.
Okay.
Yeah,
so this what you see here is a wrapper approach method where we calculated the complexity. Now, to understand the background behind this, each individual aircraft has its associated tasks. And based on the target variables, the interpolated grades here, we trained the model to give weights to each individual task. So I'll just switch back to one slide and return to this table. Just a second, please. So you can see here that each aircraft can have several tasks, okay? So when you have weight coefficients for each individual task, in the end, we have a complexity for that each individual that aircraft generates through their air traffic controller tasks that they need to do. So just for an example, I put to the right only C and P tasks, which are conflict and potential conflict. Just to give an example to the audience of that, the more tasks at hand for each individual aircraft, the higher the complexity is. For instance, this Eurowings at the top 343 has, if you remove him, you'll reduce the complexity of overall situation for 0.429. And tasks tied to that individual aircraft are just 4 categorized as number 1, the conflicts, and it has 1 potential conflict with other aircraft. So it can be seen here that tasks are definitely tied to the complexity here, and with their weights, we can ultimately calculate how they fare in the ultimate in the overall situation of air traffic. But excluding from just this removing each aircraft, we can also do another thing, and that is, for instance, you can, if you see that this Eurowings, the top aircraft 343, is the most complex to the whole traffic situation. Now, what the shift supervisor in the operation in the area control center can do is give it a STAM measure, short-term air traffic measure, that, for instance, change its route or level or anything else. Then we calculate the traffic complexity again, and we will see that tasks are probably changing with this new route, and we can effectively change not only by removing them, but by changing their route and lowering the complexity in the end, and increasing the airspace capacity with it.
Okay, thank you, Bruno.
Thank you, Mr. Kopardekar.
Okay, thank you for this interesting discussion. I would like here to just ask for a short clarification as well. When you say this complexity column that you have, is that the overall complexity of this traffic situation after the STAR measure on this particular aircraft, or is it before? What's that column?
The complexity is with all the aircraft with that one is 3.2, yeah. And if you remove it,
if you remove it, you reduce complexity by 0.429,
yes,
for example.
Yes.
So in this case, it is a highly, very big reduction in complexity,
yes.
Just by removing this one. And how many aircraft were in the traffic situation?
I'm not sure if this one. This is not probably the whole traffic situation. I just extracted the data from the table, but we can open a CSV file if we want to go into more detail to see for each individual traffic situation if you are interested.
I was just wondering if you know if the range of this complexity changes is actually from 0.34 to 0.42, then it doesn't matter very much which aircraft you remove. But if the list continues below and it is not shown here, then the choice makes a lot of. It's very important to choose the right aircraft to remove before.
Yes, but what you can do here, you can make several STAR measures applications for several aircraft, and then in the overall you will have an increase reduction in complexity.
No, I'm not asking about that. I'm just asking, is this the complete list of all aircraft?
I don't believe this is the complete list.
Okay, just for clarification.
Yes.
Okay, thank you. And now, as you may have noticed, we have opened the floor for discussion as well. So if anyone has any questions, just raise your hand, and in between the committee members will continue with their questions, and you can jump in at any time you find any topic interesting, and we will try to keep this the discussion open to all audience members and all participants. And now I would like to get back to Professor Cetek, if he has perhaps enabled his internet connection. Professor Cetek, would you like to ask a question to?
Okay, can you hear me, Tomislav?
Yes, we hear you very well.
Okay. Firstly, thank you very much for your good job, Bruno. One question regarding the classification of the traffic scenarios in the beginning of your study. You classified them as low, medium, and high complexity, right?
Yes.
And at the end of experiments, we saw that some of the C-class complex scenarios were not found to be the most complex one, but medium ones, or vice versa. What do you think? What's the reason of this variation between controllers' point of view and your classification?
Well, generally, what I was when I was doing with medium, low, and high complexity there, I deliberately, for some situations, make specific tasks. For instance, I increased traffic density, but also increased, for instance, all the potential coordination and potential conflict resolution with no conflict, for instance. And for these kind of traffic situations, they shown for some air traffic controllers that they are of lower complexity, although they are ranked within the high category because of the traffic density and the number of tasks that they have. But this was deliberately done because I wanted to prove that not all tasks are of the same complexity level. That's why you see here, for instance, several of C traffic situations that have in the medium range of complexity. You can identify them in the medium column, while intuitively you would expect that they are in the right column.
Okay, thank you very much.
Thank you, Professor.
Okay, can I ask a question as well now? You mentioned briefly in your presentation that you've done the exploratory feature analysis. So can you tell us what were the results of that analysis and how it helped you shape your model?
Okay. So first, what was done was, just a second, was a histogram of feature value distribution. So it can be seen from the histogram of feature value that almost all control tasks were represented to the same extent. However, it can be seen that there were some exceptions. For instance, first aircraft exit distance had 0 occurrences, though through all the 120 traffic situations, while some tasks such as screening were represented in more than half of the original data set. On the ordinate of the histogram, the air traffic situations here are represented, and on the abscissa, the number of occurrences are represented. As well, we've done correlation metrics between feature, which shows whether there are any significant correlations between the variables. Some features correlate as high as 0.8, and there are some weak negative correlations as well. There are some obvious high correlations between screening of the aircraft and the number of aircraft. Nevertheless, that was expected since both contain the same information within themselves, and that is the number of aircraft. However, several interesting ones, like the conflict between the first and second aircraft regarding to the distance to conflict point, correlate pretty good. Then again, we have principal component analysis was done as well, where we have the variance after just 8 components explained the 0.8 variance in principal component analysis, while the first principal component around explains 0.55 variance. And this is good because you can ultimately have, when you have transformed features in principal component analysis, you can use less features to achieve as well good result, and with that we can lower the complexity of the model. Then we've done univariate feature correlation with the target variable. It can be seen here from the graph that freedom of movement for a second aircraft that is in conflict with the first aircraft has a high correlation with the complexity scores that the air traffic controllers gave. So, which gives insight to the nature of the complexity for the performing task of the air traffic controller. So simple tasks such as conflict resolution can have multiple complexity levels that can be identified. And as well, recursive feature selection, where recursive feature selection chooses greedily the best performing features one by one. So in general, the most informative feature are the ones related to the aircraft counts, which is not that surprising. But it can be seen that the model can reach high correlation score after the combination of the first 6 features. Most of the features that contribute to the high correlation are the ones that contain the information about freedom of movement of aircraft to the left, right, above themselves, number of aircraft in the airspace, and conflict with the opposite track. So there are a lot of, I can go in more detail.
But here, why do you have a reduction? Sorry, can you get to the previous slide? why do you have this reduction in R-score with addition of other features? Do you have some correction for that, or what's going on here?
Because this is the best to be shown through bootstrapping. I'll just explain the answer to here, if I may. So there are 70 models in this slide. So each of these models has different features, and that corresponds to the ones that you saw now. If you add more features, it behaves differently in a way that maybe R-score will be lower or higher. So, for instance, a feature number 11, let me just find him on the slide. Where is 11? Okay, I found him. So it has 0.862. It only has around, I believe, 6 features or 8 related to screening aircraft count, while number 6 has around 75. Now, 74. Now, and it has a bit lower R-score. Now, why is that? Because, and why maybe we chose in the end the V6 model? Because as you add features, sometimes you can they are maybe not as informative as the ones that were that you saw the first 6, the top first 6, and that's why you lowered the R-score. But why I chose not to favor the lower feature count in the model is the reason because I believe each individual feature or task in this instance carries its own information within themselves. And the reason why for some cases like here, you can see high correlations compared to the ones that have more features and lower ones is that for the given traffic situations that the Bootstrap was testing, maybe those tasks were not represented in the favorable amount than the ones that have the aircraft count. But we all know that in the real air traffic, in the operational sense, that you will not only rely on the aircraft count and the screening of conflict and so on and so forth. It is a good practice to include all these tasks. So in the end, when we were validating on the new airspace, it was directly shown through normal distribution that more features that carry more information within themselves show that have better results from deviation from the interpolated score that controls gave than the ones that just carried the most information, the first 6 ones.
Okay, thanks for that. And just a short question about these models. How did you build 17 models? Did you just pick those features that you would like to have included, or was it just some method to that?
So earlier now I've just shown some of the exploratory feature analysis graphs and results, not all, but some. And based on those results, these 70 models were made. They were made based on expertise of the area and based on the exploratory feature analysis that we considered which, okay.
Okay, thanks. I understand now. Please, I would like to ask members of the audience also to raise their hand if they have a question. And in the meantime, I will also ask for our... Okay, we have a question from Professor Netyasov. Please, go ahead.
Thank you, Tomislav. First of all, Bruno, congratulations for a very, very interesting presentation. It was really fascinating, I would say. And it is obvious, actually, that you put a lot of effort in preparation of everything, and it's a great job. My question is maybe related to, let's say, possible usage in the industry, as you mentioned at the end. For example, what are possibility, or is there any possibility for your models to be used as a decision support tool for supervisors in the ops room, and I mean, what are the possibility for your models to predict future, let's say, complexity in future time interval?
Okay, thank you, Professor Peja. Yes, the answer in short is yes, there is a room for the operational purposes, not just by the network manager and shift supervisor, but also at the executive level of air traffic controllers and some other things. But we'll go maybe later into those answers. Now, regarding the shift supervisor, yes, it can directly be used in operational purposes because the model doesn't need to be retrained or doesn't need to be reconfigured for the new personnel or for the new airspace, which is a huge step forward in this field of research. Just because of that, it is of immense interest to the ANSPs to implement them, because it can help them use what-if scenarios for STAM measures to cherry-pick the most complex aircrafts. Also make a decision regarding the sector optimization, which configuration to use to increase the airspace capacity and reduce the air traffic controller or the air traffic complexity. And the beauty in all it is that complexity score calculated by the model ties with the answers that controllers give in the end. So yes, you can implement them in the shift supervisor position for various purposes: sector optimization, cherry picking, increasing of airspace capacity. And regarding, I believe you also asked about the prediction model, right?
Yes.
That's one problem that is not directly that was not directly done with this model, but what the model does, it can predict traffic in advance as far as you want. But there is a catch. The catch is that we all know that the further distance from aircraft from the airspace you are calculating, the higher the possibility is that their route will probably change, because we all know that field flight plans are not always they do not always result in the ones that they are flying currently, and that's the separate problem that we need to solve, not with this model. So the model works perfectly if you give them perfect trajectories, but we just need to see if the trajectory is going to change, you know. So if they change the trajectory, you need to calculate again. So that's the answer.
Yeah, thank you very much. I just to comment once, I really appreciate that the fact that you have introduced air traffic controllers in your examinations, because it is very well known that if you leave them out, probably they will not believe in your model. So it's quite good, and I would say that you are quite lucky to have them with you, and that they can help you. So congratulations once more. I don't have a further question. Thank you.
Thank you, Professor.
Thank you, Professor Netyasov. Next, we have raised hand by Petar Andraši. So please ask your question.
Okay, thank you for presentation. I just want to continue with questions regarding that complexity reduction based on the aircraft you selected. So you calculated complexity reduction solely based on removing aircraft from space, or did you try maybe shifting the aircraft position, level, or something like that?
So the example that you saw here on the slide, let me just switch back. Give me a second. Is just by removing, but the model, if you change the route, the level, or any other measure that a shift supervisor would do for STAM measures, you can do them as well. What the model needs to do then is just what-if scenario, apply this new route, calculate again, and you have a new complexity compared to this. So it can give you what-if scenarios for each STAM measure compared to the original traffic scenario. So let's say you have this, just a second. Let's say you have this traffic scenario. And if, let's say, shift supervisor, the model indicates that removing this top aircraft from entering the airspace, or maybe just changing the level to go above it, will reduce the complexity and decrease. You can in turn give 2 more aircraft to that airspace, to their airspace. You can do it. So it doesn't matter what approach you use. You can use any star measure with this approach, removing, changing route, level, speed, so on and so forth.
Thank you for your answer.
Thank you, Petar.
Okay, thanks you. Thank you. Next, I would like to ask our committee members if they have further questions. Professor Juričić, perhaps.
Okay, thank you once more. Bruno, I will go after Professor Netyasov said a very important thing about air traffic controllers. So maybe we should point out once more that your model is based according, you developed the model according to the subjective assessment of the population of 18 air traffic controllers. Can you tell us in more detail the background of the controllers? Could we use a higher number of air traffic controllers? It's a rather small sample, but we got rather good results of the model.
Yes, thank you, Professor. In the beginning, I was afraid that the statistical power of the sample will be fairly small, but it has shown that and I believe through the experiment methodology, only because of that, we got good results. And of course, it would be preferable to have more air traffic controllers. That's always the more information we have to train the model, the more reliable the model can be in regards to controllers' decisions. But I forgot what was the focus of the question.
Yeah, to tell us more about the population of air traffic controllers, and did you have some kind of dispersion of the experience, gender, or etc.? And I will continue then with just a small question afterwards.
Okay, so I made an interesting. The interesting thing about regarding the correlation between themselves here, but regarding the general population, the controllers were ranging from 3 years in experience to more than 35 years of experience in their work field. They were the same, the fairly distributed, the same, not the same, but there are a good amount of females and males in the whole data set. And a lot of things were also measured besides the complexity they were scoring and assessing. What I didn't done, but it is planned, I'll show you, would be to see for the red lines, which are, for example, females, which are males, which are the ones with high experience rate, which are with low experience rate. Then with this population score, we can maybe get another insight into how it ties to maybe a work experience and so on and so forth. But regarding the correlation of between controllers, here you can see a matrix that there are with 12 traffic situations shared between all controllers. So these are the all traffic situations that were repeated for all 18 controllers. So how similar are controllers' rankings of these situations? And we use spiral correlation here, and the number 19 is the correlation of with the controllers with the models, and the top left correlation are the graded controllers that fairly have the same scores, and the top and the bottom right are the ones that mostly deviate from each other controller. So let's say controller number 6 with controller number 18, they don't think alike at all, while controller number 12 and 6 also. So we can see that the number 6 generally and 18 do not think alike with others, while controller number 7 has a fairly similar mindset with other people that they were tested with complexity.
Yes, these results are very interesting. I'm asking that because during the validation, you did the validation only on the new airspace, but you didn't use some kind of different population of air traffic controllers. So your controllers for validation were from the same group of these 18 controllers. What would happen if we would change? What is your opinion if we would change the air traffic controllers in the validation phase?
So, I believe that the model will predict the same way. Why? Because it is built on, just a second, I'll just switch a slide. Slide number here. Because it is built on the tasks that do not rely on a human behavior or a human doing it. So these tasks, defined like this, they only are influenced by the movement of aircraft and their interaction and position. And the beauty of the tasks defined like this is that we do not look and they do not depend on how the particular one air traffic controller would resolve one conflict. For instance, you can have a situation, just a second, I'll switch again. You can have a situation with this Lufthansa and Croatia, and one air traffic controller will probably maybe resolve this same conflict just by turning them. Another will maybe give it a rate of climb and rate of descent to climb or descend them. Another one maybe will slow down one aircraft or so forth, so on. Because each individual air traffic controller will resolve the same conflict, in this case the same task, on a different way. And the beauty here is that we do not look how they will resolve it, because each individual controller will resolve it differently. We just need to calculate again when they resolved it, how the complexity, what are the tasks now once they resolve the conflict. And once they resolve, the conflict will, the complexity will change based on the new tasks generated from the new traffic pattern of the resolution of that controller.
Okay, that's the essence of your model. Great, thank you.
Thank you, Professor.
Thanks to both of you. I still see Professor Netyasov with his raised hand. Perhaps it was raised before, or maybe another question is coming. No?
No, sorry, I forgot to.
Okay, that's fine, that's fine. Next, I would like to ask as always, members of the audience, please, you can jump in at any point in this discussion. And in the meantime, perhaps another committee member who could. Okay, we have Dr. Kopardekar again with a question. Please go ahead.
Yeah, thank you again. And sorry, this is kind of interesting work, and it brings back a lot of memories from my prior work in complexity. So I apologize for so many questions.
No problem.
To you, Bruno. Thank you again. Do you think there is a minimum complexity desired to maintain the controller's attention and reduce the vigilance problem. So too much complexity is bad, but there could be some minimum complexity that may be interesting and important to maintain the attention and performance.
Okay, thank you for the interesting question, and you can ask as many questions as you like. I welcome all the questions from the audience. Don't feel bad to ask any questions. So regarding your question, Dr. Kopardekar, the interesting thing that you mentioned is that the most airborne collisions were done during the low complexity of traffic, which is interesting because usually that's coming to your answer. Usually we believe if there is a high complexity that it can endanger safety, and of course it can, but the point there is that when you have high complexity, usually controllers are on their toes and highly concentrated. And vice versa, if you have a really extremely low complexity, for instance, that you don't have to do nothing, just number 7 of the task here, just screening of non-interactive conflicts, it can lower the situational awareness of the controller, and this is not always good. Not always. This is never good. And yes, it will be interesting to see what would be the level of complexity that a certain air traffic controller needs to maintain to be on their guard all the time. In this research, this was not conducted, but definitely it can be done with this model and this task. So if, for instance, let's say there is in future some regulation that requires a shift supervisor to maintain their controllers on a certain level of awareness, you can use this to keep them on a certain level of awareness with higher complexity, but not so high to burn them.
Okay, thank you for your question and your answer. I would like to tie into this question. As we all know, we have this future program where whole Europe is actually developing the ways to automate some of the controller tasks in order to increase capacity. And this here, obviously, the same situation happens that you don't want to automate everything because then you have this out-of-the-loop effect as shown in the AutoPace project. And this out-of-the-loop effect also then, causes possible safety issues. So in this future environment, when we start automating more and more of these tasks that air traffic controllers currently do, how will your model adapt to that situation? How is it possible to adapt your model for future 2025, 2030, 2035, where some of these tasks do not exist anymore, or perhaps they are completely automated?
Okay, thank you, Professor Radišić. Yes, in the future, we definitely plan to automate a lot of things, and one of them is some of the tasks with the air traffic controllers. And how would this model fare then if you automate some of the tasks? Well, the beauty of it is what I didn't show is that the model, just a second, we use a certain set or subset of these features or so-called tasks, and these can be you can just in the future, if you automate several tasks maybe that are now not resolved by the air traffic controllers, you can just remove them from the whole concept and just use the ones that need to be used. So the beauty of the model is it is highly adaptable to any situation in a way that it can use any number of features needed for a certain situation.
So does that mean that you could perhaps use that model to determine how much will complexity reduce when you introduce a certain tool which automates some task?
Yes, definitely. Let's say, for instance, let me just switch again the slide.
I say that as it's an interesting point, because if you are willing to, if you want to introduce a certain tool which automates certain tasks, this model of yours could then give us some idea how much the complexity will reduce in that scenario.
Definitely, because let's say you want to automate, let's say, interactive conflict screening. Okay, number 5. And with that, we've seen here that interactive conflict screening. Let me just find it. It's SC. Okay, it's to the left in the in the first row, fourth column, and you can see that interactive conflict screening has affects the complexity here, and I can tell you just by the what right amount it can reduce the complexity if you automate this task.
Okay, thanks a lot for that question. And I see we have a question from the audience as well. Christina Antulov-Fantulin has raised her hand, so please go ahead.
Yes, here is Nina Antulov-Fantulin from ETH Zurich.
Okay, excuse me, just a different name is written there, so sorry.
Yes, I've connected through a different laptop. So nice presentation, Bruno. I have just one general question. So regarding at the beginning, what I see, and probably it was connected to the initial question of other professors. What you did different somehow is you did the ranking. So how do you assume that this kind of ranking of the individual tasks was changing or somehow influencing the objectivity of the scores?
First thing, I wasn't expecting my brother to ask questions, but okay. Here, thank you, Nino. Thank you for the question is good. And the answer is just a second. So several researchers here have stated and proven through their research papers that if you give a same air traffic controller a different traffic scenario, they will, not all, but some will grade them with the same complexity score. So why did I emphasize this, and why does this, I believe, is really important? Because if you plan to use the inputs from the controllers, which are not consistent with themselves, ultimately the model will not be that good, or maybe it will have some flaws in the end. With this approach, with merge sort algorithm, you've given a particular air traffic controller always 2 traffic situations to assess, and afterwards they were ranking them. And by the end of this result, they have from the lowest to highest complexity, as you can see on the picture. And I think the beauty in here is that we force them not to be inconsistent. And with that inconsistency out of the way, we can use their expert knowledge, which is really good. We need their expert knowledge we use that expert knowledge, which is now assessed good, and use it to build a good model. And that's why I believe one of the ways why the model is the results are good, not just by the features and the tasks, but also because of the experiment methodology that was used in this way. And not only that, we asked them to give them grades. We linearly interpolated these grades, which give us even more information. And yeah.
Nice. Okay, thank you. So to me, just to comment it very briefly, it looks like a quite nice pre-processing step that allows to get objectivity. Because as I see on this slide, out of the 18 air traffic controllers, you're essentially getting almost 2,000 comparisons, which to a certain sense allows you to put objectivity to this kind of thing. And yes, so this is, to me, as also a complexity scientist, these pre-processing steps is like a nice thing for the whole machine learning study.
Thank you.
Okay, thank you, Professor Antulov-Fantulin. Next up, I think we could come back to another committee member next, Professor Cetek, if you'd like to ask other questions.
Okay, I have no further questions, but one comment. Bruno told that the most of the mid-air collisions happen at low complexity scenarios. Maybe you can just try to find out what will be the complexity at such accidents or some incidents like near misses, and you can just validate that, or just you can correlate the safety and the complexity issues using this tool.
Yes, we can definitely analyze the traffic patterns that emerged during those accidents, and calculate complexity and see what was the complexity at that point. Intuitively, I believe that it will be low because, let's say, Umberlingen accident that happened mid-air collision. It was happening during the night shift, but there are some other factors that always contribute to these unfortunate events. And as I mentioned, Umberlingen here, we all know probably in the audience that it happened because that controller was switching between approach and area control, and he didn't respond in time, and there were some TICAS issues with not obeying the instructions and so on and so forth. But definitely it can be done, it can be calculated, and maybe the model, what Professor Kopardekar has mentioned, that it can be used not to reduce the complexity below that level. You know, if we find a correlation, a good correlation between those accidents and some of the complexity levels.
Okay, now you already have two ideas for further research. So if you just look at that, this was a very successful discussion. I would like to ask the audience now if you have any further questions or committee members. Professor Juričić, do you have any further questions?
No, I have no further questions. Thank you.
Okay, in that case, if there are no more questions, I declare that defense of the dissertation has been concluded, and the committee will now retire for deliberation into another room, and you can wait here for a short time, and we will come back and tell you our decision. Thank you.
Thank you for inviting me, and I had to go now, so I'll take your leave. But good work, Bruno, and appreciate inviting me. You all. We look forward to talking to you again. Bye-bye.
Thank you, Mr. Kopardekar.
Thank you, Dr. Kopardekar. It's been a great pleasure and honor to have you here. So, especially when we know that it's 5 a.m. at West Coast, USA. So, thanks a lot.
Yeah, anytime. Thank you. Bye-bye.
Bye.
Goodbye.
Brunči.
Bog, pa čekam da neko probije tu tišinu.
Da si živ.
Pa odlično si se držao. Čovječe.
Je vam bilo u redu?
Bravo, Bruno, bravo.
Ti si svjetski...
Bravo, Bruno.
Jel znaš?
Sve. Bravo, Bruno.
Svaka čast, Bruno, čestitam.
Hvala, nemojte još čestitati.
Ajde, čovječe. Tu te hvata iz nas te hvata.
Pristup ovoj sobi gdje vječaju nije baš sjajno, ali dobro, evo, će proći. Odlično, Bruno, svaka čast.
Koliko kila si lakši, Bruno?
Nemam pojma.
Bravo.
Šta to piješ, Bruno?
Javnica.
Rakiju, Feđa.
Rakiju lažira tamo u boci.
Ajme.
Domaća.
Je.
Bio si sjajan.
To je kao da se ne primijeti Jamnica, ali zna se, iskusti ove pijandore.
Mi se zadinju, Bože, ne mogu disati.
Jel ja ovo vidim ekipu iz generacije?
Je,
istina. Nikica, bez prezimena Klasić. Andreja Dumančić, pa ekipa Bog. Baš mi drago da vas vidim sve redom.
Vidiš samo njihova imena, ne vidiš ih ovako.
Ajde.
Oni su na roštilju negdje već.
Nije, vidjet ćeš i Kanita u 4.
A znala sam, svaka čast. Neke nisam vidjela od tvoje svadbe.
Jel?
Da. Sad će oni svi reći, niste se ništa promijenili, ne. A bome nisu ni oni. Jedino Andreju sam vidjela na televiziji, to moram priznat, više puta.
Koga si vidjela na televiziji?
Pa Andreju na televiziji, više puta.
Aha, Blašković, da.
Pa da.
Ne samo na televiziji, nego u novinama isto.
I u novinama, tako.
Dobiti Anita od oni velema, niste se ništa promijenili.
Da, tako je. Bruno, bio si, znaš šta?
A svjetska si nam odra.
Svjetska stifac.
Molim Engleza da mi daju ocjenu engleskog jezika.
To ćemo na samo.
Na samo?
U 4 dobar si bio.
Kako te braco iznenadio?
Pa bome je.
A ja bolje bilo da te Kristina iznenadila.
Pa prvo kaže Kristina, ja sam mislim šta?
Kako je Kristini tako mutirao glas?
Da.
Bruno, a malo je bilo problematično kad ti brat postavi pitanje, jel tako?
Pa nisam znao šta ćeš pitat. Vole, doći svašta, da.
Hvala mu napravit pa sam ti učin.
Dobro, spustit ćemo ruku.
Nešto dugo vijećaju.
Bome!
Bruno, kreni se znojit.
Kako misliš kreni?
Kaži mi, ja baš nije, ja slušam, tam nije
Onaj šuške se kao...
Imaju 2 izjave pripremljene, prošlo i nije.
Pa i ja kažem.
Pa evo sad sam ja bio do vrata, tamo su jako puno priče kod tome u sobi, mogu ti reći.
Vjerujem.
Odi preko pa poslušaj.
Ne stvar.
Halo Bruno, jesi ti to znojiš?
Ne.
Ne, dobro, samo pitamo. Ovdje je ekipa kod Kristine.
Koliko je vas tu?
6, 7, 8.
Ne znaju više ni brojati. Šta ste vidjeli?
Već počeli slaviti.
Nismo još.
Čekamo objavu samo da počnemo piti.
Oklade su pale. Evo, kladionica radi, tako da s NASom smo u kontaktu oko nekih stvari.
Ne znam, mi možemo zakomplicirati tu kompleksnost još.
Uvijek se može zakomplicirati.
Bruno, samo ti kažem kako smo mi ovdje zvali kompleksnost. Ako smemo ovako sad ovdje rekord, nemoj da neko snimati. Mi smo to zvali zajebanost.
pa može se korelirati nekako, da?
Kakva je situacija? Pa mnogo je kompleksna, jel? Šalim se. Još jednom, zaista sjajno, svaka čast. Nisam manje ni očekivao od tebe, zaista. Lepo, svaka čast.
Evo, jedino što smo se morali ovako svi sastati, ali dobro. Tako je situacija u svijetu, pa ne možemo drugčije.
Biće prilike, smo živi i zdravi samo.
Budeš ponovio sve jedno.
Može. Bez treme.
Bruno,
bombista.
evo da se i ja javim.
Pa bog.
Pa super je bilo, bravo Bruno.
Hvala.
Pozdravljam iz Splita i pokušavam brzo doći.
Kad ćeš letiti?
U 5:10 po planu.
Aha, dobro, na to očekujemo negdje oko 6, pol 7.
Ma i prije, ja ću odmah s aerodroma tamo, ja se nadam, tako da sam brzo tamo.
Može.
Eto ti.
Hvala.
Jel veselo, jer se crveniš, ne vidim dobro, nije mi toliko dobra kamera.
Pa namjerno sam uzeo low rezoluciju kameru, da me ne vidi.
Da se treba ne vidi.
Pa nego šta.
Bravo. Nisam postavljala pitanja, ali očekuj koje kad se vidi.
Pa mogla si, ja sam.
Zedam se. Ništa, pozdravljam. Biću na mute.
Može,
vidimo
hvala
se.
Andreja što si bila.
Aj bok.
Bog.
Bruno, jesi vidio moju poruku?
Ne, nisam, mobitel, notifikacije su mi ugašene.
Ne, tu na Teamsu.
Nisam ni to.
Aj, dobro, ništa.
Ček sam da vidim. A di se to vidi sad? A di je poruka? Aha, u chatu sad vidim sam malo.
Sad je gotovo.
Hvala Rusice.
To ono, dok si još bio nervozan, znaš.
Aha.
Tad sam slala.
Doris treba otići tamo u sobu i reći da kažu više lošu vijest.
On će reći da je radim pritisak na njih. On će proglasiti obranu nevažeću. Pa sve ponovno opet.
Aurora, ko je to? Bog.
I'm the fastest one.
Welcome back.
Bravo ti.
Thank you.
Evo vam piše Mira u grupu.
Stižu.
Okay, I believe we are all here. I see that Professor Cetek has some, perhaps some issues with this system now.
Actually, I'm here.
Yes, you're here. Okay, I will just please ask committee members to turn on their cameras as well, because I don't see anyone but Bruno. Okay. We can continue.
My camera is on.
Okay.
My camera is on as well.
Okay, thanks. Based on the presentation of Bruno Antulov-Fantulin, the Doctoral Defense Committee, after the public defense has unanimously passed a decision that Bruno Antulov-Fantulin has defended his doctoral dissertation entitled Air Traffic Complexity Model based on Air Traffic Controller Tasks with the grade summa cum laude. The Dean of the Faculty of Transport and Traffic Sciences will ask the Rector of the University of Zagreb to promote Bruno Antulov-Fantulin to the Doctor of Science in the scientific field of technical sciences, the field of transport technology and transport. I am concluding the doctoral dissertation defense process, and now, Dr. Antulov-Fantulin, I would like to congratulate you on your achievement, commend you for your perseverance and all the effort, time, and emotion you've poured into your thesis. Also, I would like to congratulate your advisor for taking good care of your development as a researcher and for guiding your efforts to a successful conclusion. Congratulations, Doctor.
Thank you.
Thank you. Congratulations, Bruno.
Thank you, Professor. Thank you, Tomislav, and thank you, Professor Cetek, on nice words. And it's been a pleasure to be doing this doctoral thesis and to present to all of you.
Čestitke, Bruno, i s naše strane svako dobro i Šta da ti kažem, sutra možeš duže da spavaš.
Hvala.
Veliki pozdrav.
Pozdrav, Feđa, i hvala što si
Veliki pozdrav.
Bog, Feđa.
Ćao, Feđa. Hvala ti.
Hvala ti.
Pozdrav svima.
Ćao.
Može jedan aplauz.
Čestitam, Bruno.
Hvala.
Bravo, Bruno.
Bravo.
Evo još slušača, i ovi su te slušali.
Hvala svima na lijepim riječima i što ste bili prisutni i što ste uveličali ovu obranu. Ne znam šta mi dalje, uzbuđen sam, idemo feštat.
Ništa, sad lijepo slavi to.
Idi odspavat malo, ajde, odmori sad od ovog stresa.
Ajde.
Oj, bebe.
Lijep pozdrav svima i vidimo se uskoro.
Tomu odlično si ovo moderirao. Bravo. Ćao.
Bravo, pozdrav svima.
Slatka bebica, Dejane.
Hvala.
Čestite mami i tati i sestri, bratu, to smo zaboravili.
Ajde, Bruno,
Hvala.
Bilo je fenomenalno.
Odlično je bilo, ne?
Da? Pozdrav svima. Bog.
Čekamo ideju.